All right, fluid pressure, pressure at a depth. Here we go. Fluids. This is a review. Fluid is anything that flows, right? Fluids conform to their containers. They don't have to fill them. It depends on whether you're talking about a liquid or a gas, but they will conform to their containers. In this course, the fluids that we deal with are called ideal fluids. This is like physics land type stuff. If you had me last year, you remember me talking about physics land and how all of our problems are in this imaginary realm called physics land, where we can turn air on and off, and we can turn friction on and off. And so an ideal fluid is something that is made up. It's a perfect fluid, no friction. Some of them are incompressible. It depends if it's, here again, if it's a liquid or a gas. So I want to talk about the nature of pressure in fluids. Why do fluids exert pressure? Why does this happen? What do you guys think? A static fluid produces what's called fluid pressure. Okay. They do this because of, interestingly enough, collisions, momentum, and kinetic energy. This pressure is due to collisions. Okay, so I'm going to do something here. I have this PhET sim, and if I pump a bunch of air molecules into this container, this thing's acting a little funky, but if we do this, we'll see that they will bounce around. There will be collisions between each other and collisions between the sides of the container. And those collisions are causing our pressure to increase. Because what's pressure? Pressure is force divided by area, right? So, if you have a bunch of forces acting on a particular area, you take all those little forces, you can add them up. You can get like the average force acting on a side here, right? So we can take all these, all of the collisions acting on this side. We can add them up as like an average force, which we could represent as a vector, which is going to the left, hitting this side. And whatever this area is, when we divide the two, we get the pressure on that side, right? So, pressure comes from the collisions of all of the molecules, okay? If we're talking about collisions, we're talking about forces, and so pressure is force divided by area. The forces are perpendicular to the surfaces. Okay. And as a reminder, here are the units for pressure. It's the same thing. It's a Newton per meter squared is called a Pascal. Now, I want to talk about this idea that pressure increases with depth. Okay. We humans live our lives under pressure, right? And I'm not talking about stress of a job or stress of school, but imagine yourself as a little stick figure right here. You can imagine a column of air goes up hundreds of miles, and it's weighing down on you, right? It envelops you. So we're having all of these thousands and millions and billions of collisions occurring every second, right? And the only reason we don't get squished is because our bodies have holes. Yeah? And we call this atmospheric pressure. And it is the average of all of the minute collisions happening every second on our bodies. And these are the different units that you will see for atmospheric pressure. So we're just like fish in a bowl in this sense. Now, let's say we have a block. It's floating in a fluid. Maybe it's water. Okay. Well, then we have all these collisions occurring, right? Now, how many forces are acting on this block? If it's not moving, then what do we know about the total force acting on the block? So the total force has got to be 0. The F net will be 0. Everything is balanced, right? Now here's the deal. You have forces left and right. So in the x-axis, those forces all cancel out. Right force cancels out left force. Okay, That's a thing. It's not moving left or right. So those cancel out. But the forces in the y-axis, this is kind of odd. Do they cancel out? Well, they're balanced because the block's not going up or down either, right? But would these cancel out? You see these three vectors are very long, these are very short. So something is smaller on the top, bigger on the bottom. Notice that the vectors closer to the surface are shorter. And as you go down, they get bigger, right? So we all know that pressure increases with depth. Now, why is that? Well, if you go lower in the pool, there's more water above you. That's pushing down on you. And all those, collisions are occurring on your body. And what's on top of the water? Air. So there's air above here. The atmosphere, gases have weight, pushing down. So on the top here, there's less stuff. There's more stuff on the bottom. So this is kind of odd, and you go, well, this doesn't make any sense. How are the forces balanced in the y-axis? They cancel out in the x-axis. Why are they balanced here? I have a small force, right? I can take these three forces and I can average them out to create one down force. I can take these three forces and I can average those out to create one up force. But I would have a small down force and a bigger up force. What's the deal? Well, here's what happens. We're missing a force. We need to include the weight of the thing that's being pulled by gravity, pulled by the Earth or the planet, pulling it down towards the center of that planet, probably Earth. So we have a top force that's small. We have a bottom force that's bigger. Those two really wouldn't cancel out. This thing would go upwards. But you have mg, the weight of the object. So in this picture, we're missing that force. You can create, damn it, I can't see it. Go away. Down here at the bottom of the screen, you can create that equation because everything's balanced, right? So the bottom force has got to be equal to that top force plus mg that are both going the same way. Yeah. Okay. So I'm going to go to my sketch pad here. This is the equation. Okay. Okay. These two forces were going down. This was pushing down, this was pulling, well, they were both going down, this one's going up. Now, we're going to fiddle with this, and I tried to show this in a previous video, and it was kind of a mess, so I want to redo this. Pressure is force per unit area. If we solve for force, we get pressure times area. And I can take that and stick it in right here. I can take that and stick it in right there. So we get something like this, right? And we can keep fiddling with this thing. So now instead of force, I have P times A equals P times A plus mg. Density is mass per unit volume. If I solve for mass, it's density times volume. So I can take density times volume. I can stick it right here for mass. Okay. So here's what I get. So at mg, I got density, volume, gravity. This is, should be rho, but I don't have an option on here, so I'm just calling it d. So rho vg. Okay. Now what I'm going to do next is I'm going to take this and subtract it. I'm going to move this to that side. So what I'm going to do is I'm going to take this, I'm going to subtract it over here like that. So I get this equation right here. Pressure times area on the bottom minus pressure times area on the top equals dVg. And this is the thing. Now, I can be cute again. You're going, oh my god, no, stop. Yeah, I can. Volume is area times height. So I can take area times height here and stick it in for volume right there. And I get something else. Yep, I'm going to take volume and replace it with area times height. Volume equals area times height. So now instead of dVg, I have dAhg. It's getting a little crazy. And then I cancel out all the a's. Why don't all the a's cancel? The a's cancel because if you look at our little block here, you see that it's a square shape. Both the top and the bottom are the same, it's a block, so it's the same size. Even if I do something like this, It's a circle on top, it's a circle on the bottom. So the area is the same on both sides. So all the A's cancel. I have bottom pressure minus top pressure equals dHg. And so what I did is I made this equation right here, which is pressure at a depth. P2 would be down here. P1 is up here. There's more pressure down here. There's more stuff above that point. There are more collisions, therefore more pressure. If I take P2 and subtract P1, I'm left with rho GH. This is what I was calling D in my little sketch pad. Let me go back to the sketch pad, right? So if I subtract P2 and P1, I get rho GH. P2 minus P1 is rho GH. Okay, this is called pressure at a depth. P2 is down here. P1, sometimes, a lot of times, P1 is atmospheric pressure because that'll be at the very top. It depends on the problem. Rho GH, we call that gauge pressure. H, I hate this. H is height, but it's really a depth. Okay? So, this is what's going on. It's collisions. The fact of the matter is, pressure on the top, pressure on the bottom are not the same. The forces are not the same. But this is all balanced because we actually do have balanced forces. And we can take this very simple equation right here and do some awfulness. I hope you can follow all this to get this equation, which is one of our big equations for fluid pressure. And this is the result right here.